Okay, good evening. Welcome back. One thing I wanted to tell you is I haven't received so much feedback about the lecture notes. If you use the lecture notes and find some mistakes, even small mistakes, I'm happy to receive them, even if you just correct some S or some typos, because it will be useful for everybody. So don't hesitate to send me an email if you find some typos on the lecture notes. All right, so what we have done last week, today we finished this chapter on Lebesgue measure and Lebesgue integration. So we have introduced this set of Lebesgue integrable functions on an interval, on a bounded interval. Now, with the definition I gave last week, it doesn't matter if the functions are bounded or unbounded. If they are bounded, of course, it's simpler, but if they are not bounded, we do it by approximation, and we have to be careful to take the positive part and the negative part of the function separately. But I gave the definition last week. Then we also have that if we want to integrate on a domain which is not an interval, we can do it by the following tricks. Suppose that f is Lebesgue integrable on an interval, and that you have a set which is inside this interval. We have to assume that this set is Lebesgue measurable, but we have seen the meaning of a set which is Lebesgue measurable. Then we define this integral of f on this domain as the integral of f times this characteristic function. So this function is 0 except on omega, and on omega you just have the function f. So you integrate on AB this product, and it gives you exactly this integral. So this is just a trick. Now, the next so this is the extension for domains which are not intervals. If we want to integrate a function defined on an infinite interval, a infinity, I want to give a meaning to this integral from a to infinity. What we need to do is we consider again f restricted to an interval. So we multiply by this characteristic function. So this function is 0 everywhere except on AB. And if this function is Lebesgue integrable now on AB, we can write this integral on the interval. And now if you take the limit when b goes to infinity, and if this limit exists, we call this number the integral of f on a infinity. This is true for positive function. There is no cancellation. Always think about it. When you have a function which is not positive, you may have cancellation between the positive part and the negative part. And if you have an infinite number of cancellation, you have to be careful. So for general f taking value in R, not only in R plus, we have to consider the positive part and the negative part of the function. And if this positive part has a limit, now this is a positive function. So if this limit exists in the sense given there, if the limit of the negative part also exists in the sense given there, then we can define this integral of f on a infinity. But again, we have to be careful to deal with positive part and negative part separately. And if you have already seen improper Riemann integrals, please observe, and there is a nice exercise where I encourage you to look at the examples of functions which are either improper Riemann integral on a infinity, but not Lebesgue integrable, or the converse. So they are not equal. These two sets of improper Riemann integrals and Lebesgue integrals on a infinity are not the same. So just be careful. Then this is done for infinity, but of course you can go from minus infinity to b in the same sense. And if you want to do it on the entire line, define Lebesgue integrable function on the entire line, please be careful. You first go to infinity on one hand, and then you go to infinity on the other hand. Don't try to do it simultaneously, because then you may have cancellations again. Then I mention a very important theorem, which is called the dominated convergence theorem. For this, we have to know what is pointwise convergence. When you have a family of functions, pointwise convergence means you have convergence for every fixed x. And once you understand this notion, you can understand this dominated convergence theorem. It's an exchange between a limit, j going to infinity, and an integral. You can exchange them, but you can do it only if there exists what is called a dominating function. And indeed, last week, by chance, we had an example without a dominating function, and we could see that on this example, the exchange lead to something wrong, because one integral was always 1, and when you had exchange, you got 0. So the existence of this dominating function is really essential for this theorem. Right. Everything has been done on an interval or on the half line or in line, but the theory, and you can go through it, it goes exactly in the same way. If you consider a domain of Rn, consider bounded and measurable, Lebesgue measurable set, but you can just consider bounded on either open, because open sets are Lebesgue measurable, or closed and bounded. This is enough. So for example, on a ball, you can define the set of Lebesgue integrable function. So this is a natural extension, and it's not difficult. There is another extension which is useful for what we do today and also next week. We don't consider only function with value in R, but with value in C. And a function with value in C can just be written as a real function plus I times a real function. So it's a sum of two real functions, but with a coefficient I, right? So it's, of course, if you have not seen C, you can just stay with real functions. If you have seen C, it's useful. And whenever we have an absolute value for real function, when we deal with complex functions, this is just a modulus, the modulus of a complex number. And this is why we use the same notation. Fubini's theorem is something that you are using in calculus 2 every day. Whenever, and it's important when you deal with Rn, there is no Fubini's theorem in one dimension. It allows you to exchange the order of two integrals. You can, in 2 dimensions, for example, you can exchange the integral over the variable x and over the variable y. And I gave the exact statement. Whenever you have a function of 2 variables on such a domain or on a rectangle, you can exchange the integral. And I was just finishing last week with this notion of 2 functions are equal almost everywhere. We know the meaning. It means they can be different on a set of Lebesgue measures 0. And I would like to, this is a definition. We say F is, this can be read as equivalent to G if they are equal almost everywhere. But this sign has a special meaning. This is a notion of equivalence class, and I recalled in the notes what means an equivalence relation. There are 3 conditions. So I just recall it, reminder. Is an equivalence relation is an equivalence relation if there are 3 points. F is in relation with itself. And this is quite clear if F is equal to F almost everywhere. Then you have, if F is in relation with G, then G is also in relation with F. Again, this is clear. But there is a third point. If F is in relation with G and G is in relation with a third function, H, then F is also in relation with H. This is the definition of an equivalence relation. And I thought it was completely trivial to check it for this. Be careful, the third condition is not completely trivial. There is a report already on the website about this, but you can check, or you can try to do it. it's not completely trivial. It's not difficult, but I thought it would be simpler. This notion of equivalence relation is very useful. You want to put things together. That's the idea. Do you have any question about what we have seen last week? Or either here or online, you can also ask questions. And last time I still wrote the definition of L1. And this is a very important notion. L1 of omega, but be careful, it's no more curly. L1 of omega is, by definition, the set of Lebesgue integrable function on the domain omega of this type, bounded and measurable, quotient by this. So I have to explain what is the meaning of this. It means elements of L1 are equivalence class of Lebesgue measurable functions on omega equal almost everywhere. But try to think about this. What it means if you take an element here, and usually for equivalence class, I should use this notation. F belongs to this, but I'm not going to use this notation. What does it mean? It means I don't take only one function. I take all the functions which are equal to F almost everywhere. So it means this F, I can take the function. I do it on an interval. I take this function like this. Let's say this is a F, but another one which is also the same is this function. Let's say I change it at one point. I take it, this, I take another value, and so on. The yellow one and the white one, I don't make a difference. I just identify them. This is this notion of equivalence class. So read it again. Elements of L1 are equivalence class of Lebesgue measurable function equal almost everywhere. So we don't make any difference on the yellow one and the white one. And usually we write with such a thing, which is such a bracket, but this is a general, what we use in general for equivalence class, but in this setting, we don't do it. So we write simply F in L1, but we can change F on a set of measure 0, on a set of measure 0. So it doesn't matter if you take one function and just change it a little bit on a set of measure 0, it's still the same function. This is the meaning of take this function, but you identify all the ones which are equal almost everywhere. Is it clear for everybody, this notion? We made equivalence class. You can also think like this. Instead of, okay, of course, this picture is also slightly misleading, but if you think about curly L of omega, and all these points are functions. This is F, this is G, and so on. So you just point all these functions. What we do is we take together, this is an element of L1 of omega. if all these functions are just different on a set of Lebesgue measures 0. Okay. So this was the definition. This is just an explanation, but I need to add one more thing. On L1, we define the norm, and I will recall what it is. F index 1, it is the integral I will recall in a second what is a norm. I'm just saying I associate a positive number. This is bigger or equal to 0. What is it? I take f of x. I take, if it is real, I take the absolute value. If it is complex, I take the modulus, and I integrate on omega. It's well defined because the function is Lebesgue integrable. What is a norm? Is a norm, you should think about the Euclidean distance. Euclidean distance is an example of a norm. And I have written also what it is in the notes. So reminder, a norm on I don't remember if I introduced the notion of vector space in this course. Vector space, it simply means you can add two elements, like two functions. You can make one function plus a second function. Or I just say the vector space, it means if F1, F2 belong to V, then F1 plus lambda F2 is also in V for any lambda complex. This is a notion of vector space. You can do addition of elements. You have this notion of addition. So a norm, this is what I wanted to recall. A norm on a vector space is a function. Which letter? It's a function. Let's take P. No, not P. Okay, it's a function. Let me denote it like this, because this is a standard notation. It's a function like this. V, take an element of V. Let me call it F goes to norm of F, which is in R plus. So a norm, it associates to any element of V. This is the inclusion, but in the reverse order. So I take a F in V. I associate a number which is positive, such that you have three conditions. The first one is if you take lambda F, again, lambda is a complex number. You take the no or a real number. It can also be real. Maybe I should write K just to be more general. If you multiply by an element of K and take the norm, this is norm of lambda, norm of F. And this one is just the absolute value or the modulus. This is the first condition of a norm. The second condition is what we call the triangular inequality. The sum of two elements takes the norm is smaller than the norm of the first one plus the norm of the second one. You know this from Euclidean geometry. Yeah, it's condition 3. I said there are 3 conditions. So this one, you know from geometry, if this represents F1, if this is F2, the norm of the sum, this is smaller than the norm of the first one plus the norm of the second one. This is called triangular. inequality. And the third condition, thank you, Vic, is that the norm of f is bigger or equal to 0 and equal to 0. If and only if only if. F is a 0 element of the vector space. Like for the length of a vector, you know the length of a vector is 0 if and only if this vector is 0. So this is a generalization of what you know from the Euclidean norm. The Euclidean norm, if you take a vector and multiply it by 3, its norm is also multiplied by 3. You have this triangular inequality, and you have the norm is 0 if and only if the vector is 0. Yes?
Norm is 0 if and only 0 almost everywhere?
No, this is but no, this is a point. So this is a definition of a norm. No, you cannot change it. But now, indeed, why I can say that this, I have already written this is a norm. Why I can say that it's a norm? Precisely because I'm considering equivalence class. Because the 0 element is the function 0, but it's also the function which is 0 almost everywhere. But they are put together. So indeed, this is a norm on the space L1. So I can make a remark because it's important. This, I define it, is a norm on L1 of omega, but not on L of omega. Try to think about it because this is your question. On L of omega, it's not a norm because a function which is 0 almost everywhere would have this equal to 0, but it's not the 0 function. So the function which is, take an interval, the function which is like this 1 point, 1 point. Oh, I just changed the value at 2 points. This is not the 0 function. Nevertheless, its norm, this expression would be 0. But if I want to respect this condition, I need to say that this function is the 0 function. So that's why I put together equivalence classes, a function of where the difference is of measure 0.
In this case, we can't say that that is the 0 function anymore.
Yeah, this is not the 0 function.
You should be saying it's the equivalence class of function equal to 0?
No, because here this is a general definition. Indeed, if I take V, the set of L1, I should write equivalence class. But this is just a special case. This is a general definition which holds for any V. Exercise. For any, yeah, but if you say norm, you have already a norm. So for any vector space. Exercise. And so this is for you because you haven't done any report yet. Check that this, what I have defined there, is a norm. This is very easy on L1. You have to check the 3 assumptions of a norm on this space. And indeed, if you try to look at the set of Lebesgue measurable function, it is not true because the third condition wouldn't be satisfied. And just, you can wonder, is this finite? Is this number really finite? Because I'm taking the absolute value. But remember, if F is not bounded, you have to consider separately the positive part and the negative part, which both have to exist. And this absolute value is a sum of the positive part plus the negative part, not with a minus sign. So if both are finite, the sum is also finite. So you can check that this is indeed well defined. So I define this space L1. It's a vector space. I didn't mention it, but because if you have one element here and you add a second one, the addition of two functions like this, it's going to be finite. You can check. So maybe in this exercise, there is a point 0. First, check that L1 of omega is a vector space. This is the point 0, and then you have the point 1 that it's a norm on this vector space. So if you have not submitted any report, this is an easy one. Now let me just write one more sentence. But for first year, don't try to understand it. You can skip it for now. L1 of omega is complete. I haven't defined this. I will just write it in one sentence, but without giving too much explanation. It means any Cauchy sequence. I haven't defined this. I gave the definition in the notes. Just for, oh, they want to know what is a Cauchy sequence. You can explain. Just an example, just to give you a feeling. R is complete, but Q, the set of rational number, is not complete. This is a big difference between R and Q. If you take a sequence of numbers in Q, you may converge to something which is not in Q, an approximation of pi. Take an approximation of pi. Pi is not rational, but you can be as close as you want from pi, or square root of 2. So Q is not complete because some sequences converge only in R and not in Q. The same here. You can take a sequence of functions in this space. If you take a limit, this sequence converge inside. So this is a notion of complete. It converges inside. If you are interested, you can look at the definition of Cauchy sequence. It's not important, but I wanted to say that it's complete like R. It contains even the limits of all sequences. Okay. And just for information, a complete norm space. We have a norm, and as I said, it's complete, is called, just in case you see this name, is called a Banach space. This is the name of a guy. No, I don't think he's French. I guess he's German, but I'm not sure. You can check. That's just a name. Whenever you have a vector space with a norm and which is complete, it's the best situation, like the set of real number, it's called a Banach space. So R is a Banach space, L1 is a Banach space, Q is not.
He's Polish.
Okay, he's a Polish mathematician from Poland.
Polish.
Okay, now let me just make a parenthesis. a long time ago, when you were very young, I introduced L1 log of Rn. You remember? And I said, I cannot give you the full definition right now. It was in chapter 1, simply because I had not introduced this. So now you are 2 months older than 2 months earlier. I can give you the definition of this. By definition now, it is a set of F from Rn to K, or real or complex, such that for any omega inside Rn, omega bounded and measurable. So it's a nice set, like open set or a ball. F times this guy. Remember, this product is a function which is 0 everywhere. No, it's a function which is 0 outside of omega. So this belongs to L1 of omega. So it means locally on any set omega, this function is L1 in the sense. Okay. So in particular, it means you can change this F on any measurable set of measure 0. It's the same function. And probably I use it. I said take the function x goes to 1 over x. Of course, you have a problem at one point. Just change it and say with, so if I call this F with F of 0 is 0, I'm changing the function just on one point. This function F, okay, it's not, this is if x is different from 0 and F of 0, you take it 0. This function is in L1 log. It's not integrable. No, sorry. No, sorry. I'm saying something wrong. This is not in L1 log. No, it's not. Can you see that it's not? Why?
Okay.
No, this is not correct.
No, that's not correct. That's definitely not.
This is not correct. Sorry. But so let's take. Okay, what I wanted to say with this example is that I can change a function on a point. Let's take another function which is in L1 log, but not in L1. Now a much simpler example. Take x goes to x squared. I take this f, polynomial. This f belongs to L1 log of R, but of course, f does not belong to L1 of R. You cannot take its integral. It would be infinity. But locally, look at this function. The function looks like this. Take any omega. Take any omega. Then this function, if you come back to calculus 1, this integral on the interval is just this area. And this is finite. So this function is in L1 log, because locally you have no problem, but it's not integrable on the entire line, of course. But yeah, this, unfortunately, this is a counterexample. This one is not even in L1 log at 0. Yeah, even if you change it as 0. Yes. Okay, so now we have a full definition of this space, but you can see when I introduce it, we had not introduced the notion of Lebesgue measurability. We had not this notion of almost everywhere you can change a function on a set of measure 0. Now we understand it. So we know what is L1 for a bounded omega, and L1 log means on any bounded unmeasurable set, this function, which is 0 outside of omega, is in L1 of omega. Okay. There is one exercise which I also encourage you to do. Difference between pointwise convergence and convergence in L1. I will explain what it means. It's more explicit, but let's try just to see what it means. What is pointwise convergence first? So you have to take a sequence of functions. So I take fj, j in n, and each fj is, let's say, from omega to k. So you take a family of functions. What means pointwise convergence? And we introduced and discussed it last week. This sequence converge pointwise if for any x inside omega, the limit fj of x, limit when j goes to infinity of fj of x exists. So you see, I fix a x. Now, when I fix a x, these are just numbers. And I'm assuming, this is the notion of pointwise convergence, I'm assuming that this family of numbers have a limit for any x. Think about it, pointwise convergence. Now, what means if this sequence converge in L1 of omega? Now I have not defined it explicitly, but you can guess it from the definition of the norm. If there exists f infinity, exists a function, I can write it in L1. Such that, who can tell me the end of the sentence? So limit of what? No, there is no x. Who is fjj? There is no fjj. No, if the difference between fj minus f infinity, and I take, this is an element of L1, this is an element of L1, instead of doing the sum, I can make the difference. And if this, I take the norm L1, which is this integral of the absolute value. So maybe I can write it explicitly. I can even write a formula. This is limit when j goes to infinity of this integral on omega of fj of x minus f infinity of x dx is 0. But it makes a big difference. Look here, I do it only pointwise. Here I take so it means this difference, of course, has to go to 0, but in such a way that the difference is even integrable. So there is an exercise about this, I don't remember the number, but where you can test on a very explicit example that these two notions are different.
So shouldn't it be like fj dot minus f infinity dot?
No, because I take the integral, I take fjx, f infinity x, but I integrate over x. Or this is the same, but you can write it like this, but fj, if you want to dot, minus f infinity of dot 1. But I mean, these two things are exactly the same. I just don't write the dot. So please, it's not a difficult example because you can really check this condition explicitly. You can even compute this integral. So you can do everything. All right. So far we have defined L1. Now we know who is this guy. Who is LP? For P, any number bigger or equal to 1. Of course, the case 1 is already known, but who is LP? So it's a generalization. And this is very useful because next week we are going to speak about Hilbert spaces, and L2 is a very useful space. So what is the definition of LP? It's very close to what we have done so far.
Put the norm to the p power
Not the norm power P. So definition.
like the norm itself.
For P bigger or equal to 1, LP of omega, it is a set of F from omega to K, so that F is, of course, Lebesgue measurable. Otherwise, you cannot do anything, but this is satisfied by almost all functions. It's Lebesgue measurable, and the integral of f of x power p dx is finite. So at every x, you take f of x, you take the power p, power 3, power 4, or power 1/3. No, it's bigger than 1. So 4/3. You don't need to take an integer. And you integrate. Just to give you an example that makes... let me finish the definition. LP, the endo. Oh, no, sorry. Sorry, I'm doing a mistake. This is true, but I do the same as before. It means if two functions are equal almost everywhere, if you can change them on a set of measure 0, you just put them together. You don't want to distinguish functions which are 0, which are equal almost everywhere. So I put them in the same box. And we endo LP of omega with a norm with norm, the norm of f index p is this integral on omega of f of x power p dx, but this is not good. Of course, this is finite by definition, but I don't take this. I take the piece root of it. Can you guess why I need this piece root? No, not the triangle. The first inequality, the first condition. Remember, we want a norm to have this property lambda f. Any norm has to be lambda and norm of f. This is the condition on the norm. If you forget this power 1 over p, take lambda times f, you are going to get lambda power p. And this is not what you want. So you need to take this piece root in order to get this. So this is the only thing. Let me show you on an example that it makes a difference. Example. I just want to show you a small example. I'm going to take immediately a half line. So I'm cheating a little bit because I said before this set is bounded, but we know that we can extend it. The function f x goes to 1 over x. I'm not around 0, so I'm looking at what happens at infinity. It is not in L1 of 1 infinity. Try to integrate it. You will see it's infinite because it's a logarithm and that's it. But f is in LP of 1 infinity for any p strictly bigger than 1. I let you think about it. If p is a little bit bigger than 1, this function is integrable. Think about it. It can be an exercise to check this. It's easy. So it means there is really a difference between L1 and some LP. And of course, it's easy to find a function which is in LP, but not in a LP prime. So if you want to make a picture, remember the biggest set. The biggest one is L1 log. I told you it's a very big set. But inside, you have one piece which is L1 of, okay, let's take, Rn. You have L2, and let's say you have a L 3.14 of Rn. I don't have to take an integer. There are people inside the intersection, and some are either inside or outside of the other one. So you don't have any full overlap. By the way, who could be inside this one? Can you guess? A set of functions that we have seen. No, constant functions are not in any of them. Try to integrate the constant function on R. Yes?
1 over x squared.
No, I want a set of functions, not an example.
Take the test functions and become.
Yes, for example, here inside, we have the test function on Rn. You can, or also the Schwarz function I introduced a long time ago. The Schwarz function or the test function are in all these spaces. So there are people inside this intersection. You can take the integrals of these guys on any of these spaces. Just wanted to tell you that I define LP like this. They are not contained in each other. There are people in the intersection, but you have also people outside of each other. But now you should complain about one thing. Or don't complain that it's too difficult.
Isn't zero?
Where is zero?
Isn't it not the zero integral zero?
Zero is somewhere inside here, the zero function. Okay, it's a very special constant function. All the other constant functions are here, constant function. They are not in any LP, but they are in L1 log.
Also, Professor, could P be any real number greater than like greater than 1? Any real number.
But yes, I didn't assume that they are integers. That's why I put 3 or 314. Yeah, it just said P is bigger or equal to 1. I didn't say that it's an integer. It can be any real number. Yes. That's why I put exactly this one. So you can even take L of pi if you don't want to. This is possible. Yes.
What is the problem with P smaller than 1?
I don't think you can check the triangle inequality. I think this is a problem. Check, but I think so. Yeah, but still, we can work with these spaces. They exist, you can define them, but the norm is a little bit, it's not a norm. You have other properties. I said before in the definition that Fp, when I just recall the definition. I said this is a norm. Is this true? Yes, it is, fortunately. Thank you. Okay, it was not, now it is. Yes, thank you. Is it a norm? The answer is yes, but remember, we have to check that the norm of F1 plus F2 in P is smaller or equal to the norm of F1 T plus the norm of F2 P. This is triangle inequality. If P is 1, this is fine. It's easy. Try to do it with P different from 1, except if you are really a genius. Otherwise, it's difficult. So I'm going to give you 2 inequalities which help. But yeah, proving this, not easy. So let me give you enough information, let's say, enough information for proving it. If somebody wants to do it, I would be happy. I'm not going. Beta, you haven't submitted any report. So this is a good exercise for you. Proving that LP is a norm space. But you need 2 ingredients. Be careful, it's not easy. So it's based on truth. The proof is based on 2 results, which I'm just stating. If somebody is interested, the proof is in the book I'm using, but it takes some time to do it. The first lemma, which is sometimes useful, take any number A and B bigger or equal to 0, and take yes, real numbers bigger or equal to 0. And alpha, beta inside 0, 1 open, but of sum equal to 1. Then I want to compare the product AB and the sum A plus B. Of things are missing, be careful. I would like to compare this in an efficient way. And it turns out that this is true. Alpha 1 over alpha, beta 1 over beta. It's not trivial. This is doable, but the product of AB is smaller than the sum of A and B, but with this arbitrary coefficient, as long as alpha plus beta are equal, alpha plus beta is equal to 1. This is an inequality which is sometimes useful. So the product of two numbers can be smaller than a sum, but with these arbitrary coefficients satisfying this. This is the first technical lemma. This can be proved. The second ingredient, you can try, if you don't believe me, take any A and B, take any alpha and beta satisfying this, compute this, and check this is true. But this is a small technical result. The other one is very important. It's a theorem. And one student has already used it in a report. It's called Hölder inequality. Take two numbers, P and Q, bigger or equal to 1, with 1 over P plus 1 over Q is equal to 1. In fact, if you take P, a real number bigger than 1, there exists only one Q which satisfies this. You can solve this equation. There is P and Q are called conjugated. Take any number satisfying this and take F in LP of omega and G in LQ of omega. That's why I wanted to define LP and LQ for any positive real number, because as soon as, even if P is an integer, Q is not an integer. You can check. What is the conclusion then? F times G, you take the product of two functions. It turns out that this belongs to L1 of omega. And the norm of FG1 is smaller than norm of FP times norm of GQ. I know these two results are a little bit technical. They are useful. This Hölder inequality is very useful. Look what it means, and I will come back to it next week. Take function in a certain space. Remember my pictures before. We had these spaces LP, LQ. So I take one in LP, one in LQ. The product is in L1. And we have this, the norm of this one, this product, so this is a norm 1 because it is in L1, is smaller than the product of the norms. If you have these two ingredients, in fact, you need this ingredient for proving this. And once you have this, you get what we want. And this has also a name because it's important. It's called Minkowski inequality. He's not French. I don't think so. Minkowski inequality. If F and G both belong to LP of omega, then norm of F plus G index P is smaller than norm of F power P plus norm of G index P. This is what we wanted, because this implies LP is LP of omega is a norm space. This is a condition which we need for a norm space. So these three blackboards are a little bit technical, but I wanted to mention, to use this story. First, you need this small inequality just with numbers. Look, here this is only with numbers. You are playing with A, B, and alpha, beta. There, you play with two functions which are in two different spaces. But if P is related to Q with this relation, then the product is in L1, and you have information about the norm. And what we really need, Minkowski inequality said that the norm of F plus G, the norm P, this is called the P norm, is smaller than the P norm of F plus the P norm of G. And once you have this, you know that LP is a norm space. Okay.
You only need one, right? And you get the other inequality. But
I don't understand.
I think like you get each inequality through starting with one inequality.
You start with this, then you can prove this one. Once you have proved this one, you can prove this one. It goes in this. And it turned out, I could write it plus LP of omega is a Banach space. It means, again, it's complete, but I don't put too much emphasis on this. Just what happens if you choose P is equal to 2? Can you tell me who is Q? Yes. So it means if you take P is equal to 2 and Q is equal to 2, look what we obtain. We obtain that if F and G are in L2, the product is in L1, and this L1 is smaller than the norm of F in the 2 norm and the norm of G in the 2 norm. Next week, this will be the starting point for a Hilbert space. I don't want to write it because we will come back to it tomorrow, next week. There is one space that you mentioned a few, maybe 2 weeks ago, Dominic, the L infinity. I need to introduce L infinity. One more space, or one last space, L infinity of omega. Who is L infinity? I haven't, infinity is not included into R. So when I write P bigger than 1, it does not contain infinity. So I need to define who is this guy. I have already introduced this one, curly, just bounded, but I haven't introduced this Roman L infinity. So I need a definition. A function that F be a function from omega to R. Here I consider real, be careful, be measurable. what is the essential sup? So be careful, it's E double S, and then you put one more S like this. So it's called essential sup. Essential. What is the essential sup of F? No, nothing to do with support. Of course, it has to do something with supremum. What we want to have. Consider this function. Because one of you like constant function, I take a constant function, but I change it at some points. Just at a few points, I change it like this. Okay. So I change this constant function on a set of measures. Oh, let me give an example. Take f of x, f on 0, 1. From 0, 1 to r. F of x is equal to 1 if x is not equal to 1 over n, and it is n if x is equal to 1 over n for n any natural number. So the picture is slightly different. It's a constant function near 0 and between 0 and 1, but I change it at every fraction, 1 over n, I give the value n. It's a well-defined function, right? Check, it takes the value n if x is 1 over n.
And you put that not equal to.
So it's not equal to, thank you. Now it's a good function. So is this function bounded? No, because it takes arbitrary large values. So this is not bounded, right? Nevertheless, it's almost always 1. So I would like to say, oh, if you forget a set of measures 0, this function is bounded by 1. This is the notion of essential sup. So how can I define it? It is an infimum over all m real, such that f is smaller or equal to m almost everywhere. Let's check if it is meaningful. I take a m. Take a m here. This m satisfies this condition. F is smaller than m, except on a set of measure 0. But I can take a smaller one. This is m prime. It's still true. And I can go down until this m double prime. You go down a set of measures 0, but at 1 you have to stop. Because if you go to a smaller value, then this is no more true. So for this example, the essential sup of f in this example is 1. It means I just forget if the function is bigger than m on a set of measure 0. This is this notion of essential sup. You take all m such that the function is smaller than m almost everywhere, and you take the minimum value of m, infimum over all value of m. And so you can guess the essential f, the essential inf of f you do on the opposite way. You take a value smaller than this one. If this m is smaller than the function almost everywhere, you move up. So it is the sup on all, like, use small m real such that f is bigger or equal to m almost everywhere. It's not completely trivial, but if you think about it, it's a good notion. You want to eliminate sets of measure 0. So if you have this picture in mind, it helps. So we can also think about the maximum up to a set of measure 0 for the essential sup. It's not so precise, but it's maximum up to a set of 0 measures. Doesn't matter if it is bigger on a set of Lebesgue measure 0. So now I can define L infinity. L infinity of omega it is a set of function f from omega to k. So be careful. I define the essential sup for real functions. Now I take either real or complex such that f is Lebesgue measurable. This is always the same Lebesgue measurable. And the essential sup I cannot write f. That's because, as I said, it was defined only on real numbers. So what I can do, take the modulus. Essential sup of either the modulus or the absolute value, now this is real, is finite. And as before, equivalence class modulo function of which are different on a set of measure 0. So this function would be in L infinity because its essential sup in this sense is 1, which is finite. So you wanted to have this definition, now we have it. And as before, this is a set of function. I want to define a norm on it. What is the norm on it? Yeah, I just take this essential sup. We set the norm infinity of f. By definition, I take the essential sup of this absolute value. This is smaller than infinity for any f in L infinity of omega. And there is a problem?
I'm just working on the piece of notation for the equivalence process again, but it is what is normal.
Yeah. And it defines a norm on L infinity. In this case, it's much easier to check that f1 plus f2 norm is smaller or equal to norm of f1 plus norm infinity of f2. You can do it by yourself. This is easy. Check. I told you it was not easy for p. It was easy for p is equal to 1. For p is equal to infinity, it's easy again. In between, it's not easy. And again, L infinity of omega is a norm. We have a norm, it's a norm Banach space. I just mentioned it.
It's always known.
By definition, you need a norm.
In that case, the word non.
You can forget it, it's a Banach space. Yes.
Exactly.
Yes. All right. Any question? Yes. The answer is yes, but you have to do it in the correct way. Yes, it converges. The question is, you can try to do it as an exercise. Do we have f t converge to norm f infinity when p goes to infinity? Is it meaningful first? If you want to give a meaning to this, you need a f which is in all of them, because you want to take the norm of f in any LP space. So you need to take a f which is really in this intersection. So for example, take f, I guess take f in the Schwarz space, or also in the test function. And try to think about this. And the answer is yes, for these functions, you have such a convergence and you can check it. But, or you cannot do it for arbitrary f because it's not meaningful. Okay, so you can think about this. Any other question about L1, LP, or L infinity? These spaces are useful. You know, this is really, think about the title of this course, functional analysis. It means we do analysis, we do calculus, but on families of function, not only on one function. Calculus is you deal with one function. Now we deal with families of functions. L1 function, L2 functions, or LP functions. All right, I wanted to finish this chapter today. I'm not sure I can do it, but let me just do the final part. This is 2.2 only. I'm surprised with the number. Okay, so there is a mistake in my note. Approximation. In LP spaces. Okay. What do I mean by approximation? Remember, an element f in LP, let's say 0, 1. Let me take the 0, 1. It's something very complicated because you can have something, no, I can change it on a set of measure 0. No, sorry, it's too complicated. Let me take a continuous function and again, delete a few points. Okay, this is an element of LP, Y2 LP. But I'm not very happy with this element because why should I care about these 4 points or 5 points? I would like to say, oh, it's much better to take this function which is continuous. Can I always take it? Why? Yeah, but in the equivalence class, do we have one which is continuous? Not always. For example, if I take really a function which is discontinuous, I cannot take one in the same equivalence class which is continuous. So it's not true that you can always take a continuous one. So let me give you the final statement, and then we will explain how to construct this. So let me give you directly the final theorem, and next time we will go through the 3 steps. So the final theorem is the following one. For any p bigger or equal to 1, just be careful. P is, I don't have to write it, but I don't just want to emphasize. P is equal to infinity is not bigger than 1. So I don't need to write it, but I want to emphasize it. For any f in LP of omega, and for any epsilon bigger than 0, there exists a G in LP of omega, G continuous on omega, such that the difference between F and G in the norm LP is smaller or equal to epsilon. This is the best you can do. What does it mean? Take any element which is nasty, the white one. It has, I do another example with some jumps like this. This is a function. This is A. What the theorem says is you can find, for any epsilon, you can find a G. It's going to be like this. Probably you just forget this point because it is of measure 0. And let me continue like this. So F is a white one, G is a yellow one, and it says the difference in the norm LP. So the difference, you can measure it. It is a small difference. You can almost not see it, but this is a small difference in this area in the P norm between these 2 functions. You can make it as small as you want. So you can approximate any nasty function in LP by a 1, which is also integrable, but in addition, which is continuous, such that the difference is smaller than epsilon in the right norm. Is it possible for P is equal to infinity? No. Because take a function, a characteristic function. This function is in at infinity. If you try to approximate it by a continuous function, this difference will be more than epsilon. You cannot make it as small as, in fact, it will be of difference 1 or 1/2 maybe. But so it doesn't hold, be careful. Not true. The statement is not true for T is equal to infinity. This is why I emphasize it at the beginning. But this is a very useful theorem, especially when you do numerics. Because, of course, numerics, you have problem with continuous function, but if your function is very nasty, you can still find a better one, which is up to a difference of size epsilon, as close as the first one. How do we prove it? Yes.
I think in the drawing you should have an area of 0 in the middle, right? Because the 2 functions cancel.
Yes, here I can, because it seems that the white one is continuous, I can just take this, where,
So when you say the difference of f minus g, that's a function, right? Now that's
yes, it's a function, but then I take the LP norm. So the LP norm, if you think about this norm, it's a kind of surface with a power p between these two functions. You take the difference. Think about what is the meaning of this. I'm claiming, at least on this picture, I can represent this difference as a kind of surface between these two. It's exactly the surface if p is 1. If p is different from 1, it's a little bit different, but it's essentially the same. So this is a theorem you should remember. Even though the functions are not very nice, you can approximate them by continuous function up to an error of size epsilon. And I will just sketch the proof next time. I will spend 15 minutes on this, but let me just give you the 3 steps. Then proof in 3 steps. The first one is, so I'm considering any f in LP, approximate f by a bounded function. Let's say fb. Because this f might be unbounded. I mentioned at the beginning in Lebesgue measurable function or Lebesgue integrable function, you have some which are unbounded. So the first step is to approximate an unbounded one by a bounded one, up to an error of size epsilon over 3. Then the second step is approximate. I will come back to this quickly next time. Approximate fb by a simple function. You remember what is a simple function? Who does not remember what is a simple function? What is a simple function? You like asking questions. What is a simple function? A simple function is a function made of characteristic functions. It has this shape. The simple one, so it's on a measurable set, you put a constant. On a different measurable set, you put a different constant, another constant, and another constant. So you approximate a bounded function by a simple one. And what I mean, you have, of course, my pictures are continuous. Or I do an approximation by some continuous function, by some simple functions like this. And then okay. It's an approximation by simple function. And you can do it again up to an error of size epsilon over 3. And the third step is approximate simple functions. I should give a name. By a simple function fs, because it's simple, approximate the simple function fs by a continuous function. So this is what I said, or what I represented here. I have a simple function like this. Now I approximate it by a continuous function like this, such that the error is of size epsilon over 3. So if you do these 3 steps, here you lose an epsilon over 3. Your approximation is of size epsilon over 3. Then you approximate fb by a simple function. Again, you lose epsilon over 3. Then you approximate simple function by continuous function, you lose epsilon over 3. If you do this process altogether, you lose epsilon. So this is what we call an argument by epsilon over 3. You have 3 steps, and at each step you lose something. So I will just come back to this next time, and then we finish this chapter. But again, this is useful for approximation. And the main result is this: for any LP function, you can approximate by a continuous function. Okay, that's all for today. Any question or remark?
And then functions outside of big set.
Yes, I mentioned one today, 1 over x. 1 over x, the most stupid function, is not in L1 lock. So yes, there are functions which are outside. And of course, you can always imagine functions which are more complicated than any set of functions, but it depends on what, I mean, we are using this very often. So it depends on what you do. But yeah, this one is not in L1 lock at 0.
By the way, 1 over x squared or x to the whatever bar is not in L1 lock.
Yeah, you can take, if you take a square here, you have the same problem, or any power.
Then people say,
Any other question or remark?